Pluto, once considered a legitimate planet in our solar system, remains a captivating and perplexing dwarf planet situated far from Earth. Despite its former classification, recent bold assertions by esteemed astrophysicists Neil deGrasse Tyson and Michio Kaku have stirred new interest in Pluto. They have suggested that Pluto's frozen world could be on a trajectory toward a catastrophic collision with Neptune, prompting a flurry of questions about the plausibility and consequences of such an event. Could this scenario be an exaggerated theory, or is there a legitimate cause for concern? Let's explore the potential ramifications of a Pluto-Neptune collision. Initially classified as a planet, Pluto was reclassified as a dwarf planet due to its irregular orbit, and this decision has kept it a subject of ongoing debate in astronomical circles. The latest studies by leading scientists suggest that Pluto's orbital path dangerously intersects with Neptune's, raising alarm about the possibility of a deadly impact. Given their proximity in their respective orbits, can a collision between Pluto and Neptune actually happen? And if so, what would the implications be? Pluto's journey around the Sun is unlike that of any other planet in our solar system. Its orbit spans an intricate 248 years, which means that since its discovery in 1930, Pluto has yet to complete even one full orbit. But the unusual nature of Pluto's orbit doesn't stop there. It follows an elliptical path that deviates significantly from the near-circular orbits of most other planets. To further complicate matters, Pluto's orbit is tilted 17 degrees to the ecliptic plane, making its trajectory much steeper compared to other planetary paths. An especially intriguing feature of Pluto's orbit is its intersection with Neptune's. For about 20 years during each of Pluto's lengthy orbits, it comes closer to the Sun than Neptune, a strange anomaly that contradicts the usual positions of these two planets in our solar system. This raises the important question, why haven't Pluto and Neptune collided yet? The answer lies in the powerful gravitational forces from other bodies in the solar system. After Pluto was discovered, astronomers quickly recognized the oddity of its orbit. Unlike the nearly flat orbits of the other planets, Pluto's steep angle and elliptical trajectory were starkly different. The complexity of its path became even more apparent as scientists realized Pluto's orbit crosses Neptune's. Despite these unconventional characteristics, Pluto's orbit has remained surprisingly stable, thanks to the gravitational effects from other celestial bodies. The three-body problem in celestial mechanics seeks to explain the interactions and movements of three bodies, such as Pluto, Neptune, and the Sun. Pluto's path through space can be erratic, as even slight changes in its initial conditions can result in drastic alterations in its trajectory over long periods. However, simulations have demonstrated that Pluto's orbit has remained steady over extended time scales, indicating that its path is not as chaotic as it may initially seem. The significant gravitational pull from massive bodies like Jupiter plays a crucial role in stabilizing Pluto's orbit for billions of years. These forces are essential in maintaining the overall order of our solar system and preventing any potential chaos. While Pluto's orbit demonstrates an intriguing balance of stability and chaos, it's important to recognize the inherent challenges in predicting the movement of celestial bodies, especially those with irregular orbits. Although numerical simulations can provide valuable insights, they also emphasize the unpredictability of space events, making long-term predictions uncertain. The concern raised by astrophysicists like Tyson and Kaku about a potential collision between Pluto and Neptune may seem far-fetched, but their warnings have caught the public's attention. If such a collision were to occur, the consequences could be disastrous for our solar system. The impact would release a massive amount of energy, likely leading to Pluto's destruction due to its small size and icy composition. The resulting debris could pose a significant risk to nearby planets and their moons, including Earth. The effects of a Pluto-Neptune collision would not be limited to Pluto alone. For Neptune, the collision could dramatically alter its atmosphere and orbit, depending on the nature of the event. Michio Kaku, an acclaimed theoretical physicist, offers a unique perspective on this topic. His extensive research into string theory and celestial mechanics suggests that understanding Pluto's orbit could yield valuable insights into the physics governing space exploration. By examining the gravitational interactions shaping Pluto's orbit, we can gain essential knowledge for future space missions. This knowledge could help scientists better prepare for potential space threats and aid in the exploration of distant regions of the solar system, as well as beyond. The principles derived from Pluto's orbit also have broader implications for the study of other dwarf planets and trans-Neptunian objects. Pluto's complex orbit challenges our understanding of planetary motion, reminding us that space is far more dynamic and unpredictable than we often perceive. The connection between celestial mechanics and string theory highlights the importance of understanding how planets and other celestial bodies interact. If Pluto and Neptune were to collide, it could become a landmark event in cosmology, offering a rare opportunity to explore string theory's predictions under extreme conditions. This collision would release vast amounts of energy and could potentially offer a glimpse into the behavior of elementary particles and forces at high energy levels, a major focus of string theory. Although the direct impact on Earth would likely be minimal due to our distance from the outer solar system, the broader scientific implications would be profound. Such a collision would provide new opportunities to explore the universe's fundamental nature, particularly in areas relating to string theory and theoretical physics. The unusual orbit of Pluto continues to capture the imagination of both astronomers and space enthusiasts, and the ongoing debate over its status as a dwarf planet has reinvigorated interest in its role within our solar system. The concerns raised by Tyson and Koku underscore the complex forces that govern the movements of celestial bodies, emphasizing the importance of understanding gravitational influences and orbital mechanics. These forces are vital for comprehending the dynamics of our solar system and the ongoing debate surrounding Pluto's status as a planet. As scientific instruments and observational techniques continue to evolve, our ability to monitor and simulate the movements of celestial bodies like Pluto becomes more refined. High-resolution telescopes, both ground-based and in orbit, offer unprecedented views of distant planetary objects, revealing intricate details about their composition, atmosphere, and motion. These advancements are crucial in assessing potential risks, such as planetary collisions, and informing accurate long-term predictions of orbital trajectories. One particularly promising avenue of research is the integration of artificial intelligence and machine learning into astrophysical modeling. These technologies can analyze vast datasets and simulate complex gravitational interactions with higher precision than traditional methods. By applying these tools to the study of Pluto's orbit and its resonance with Neptune, scientists can uncover subtle patterns and predict anomalies that may otherwise go unnoticed. Moreover, the discussion surrounding Pluto's classification has sparked renewed interest in the criteria we use to define planets. The International Astronomical Union's 2006 decision to demote Pluto from planetary status was met with both support and controversy, igniting debates among scientists, educators, and the public. This controversy reflects a broader philosophical question within science: how do we define objects in an ever-expanding universe filled with exceptions to every rule? Many experts, including Tyson and Koku, argue that our definitions should evolve with our understanding. The discovery of other large objects in the Kuiper belt, such as Eris, Haumea, and Makemake, challenges the uniqueness of Pluto and compels astronomers to reconsider how planetary status should be determined. Should size, orbital dynamics, or geological activity be the determining factors? Or should we accept that the diversity of celestial bodies requires a more nuanced classification system? Regardless of its status, Pluto remains a symbol of the outer solar system's complexity and mystery. It has become a gateway to the study of trans-Neptunian objects, the Kuiper belt, and even the hypothetical Oort cloud, a distant region believed to be the source of long-period comets. These outer realms, though far removed from Earth, hold vital clues to the early formation of the solar system and the dynamic processes that continue to shape it. Future missions to this distant frontier are already being proposed. Concepts such as the Kuiper Belt Object Explorer and follow-ups to New Horizons aim to delve deeper into these icy regions, conducting flybys of additional dwarf planets and collecting more comprehensive data. These missions would not only expand our knowledge of Pluto and its neighbors but could also uncover entirely new celestial phenomena that challenge our current scientific models. Ultimately, the study of Pluto, its orbit, composition, and potential for interaction with other planets, is more than an academic exercise. It exemplifies the spirit of scientific inquiry, encouraging humanity to look beyond the familiar and confront the unknown. The possibility of a Pluto-Neptune collision, however unlikely, invites us to ask bold questions, seek clearer answers, and remain ever curious about the workings of the universe. Comprehension of the motion of the planets and the development of a region known as the Kuiper Belt beyond Neptune, where tiny icebergs and bodies reside, has significantly advanced. Understanding Pluto's orbit provides valuable clues about the gravitational interactions that may have shaped the early offering of the solar system, essential data for the future of space missions focused on exploring potentially habitable worlds outside of our solar system. Although the likelihood of a Pluto-Neptune collision remains extremely low, research into these celestial objects serves as a reminder of the universe's ever-changing nature. As we continue our exploration of the far reaches of our solar system and beyond, the study of planetary orbits and celestial mechanics will remain central to our exploration efforts. Pluto's unique orbit offers valuable lessons about the planet's complexities. Motion and the forces that shape celestial bodies have continued to do so over time. Investigation of Pluto's orbit and its encounters with Neptune serve as a reminder of the erratic nature of the universe. With each new discovery and theoretical model, we expand our comprehension of the universe and advance insights into the mysteries of distant worlds. The study of Pluto's orbit not only provides answers about this distant world but also helps us predict future trends in celestial behavior, contributing to a better understanding of the forces that govern our solar system and beyond. In conclusion, the possibility of a Pluto-Neptune collision, though highly unlikely, underscores the dynamic nature of the universe. The study pertaining to Pluto's orbit and interactions with the gravitational forces exerted by Neptune offers valuable insights into celestial mechanics. As we continue to explore these distant bodies, we refine our models of planetary systems and enhance our ability to predict future cosmic events. The potential for discoveries in this field is limitless. Additionally, as technology advances, so will our ability to study and comprehend the vast, ever-changing cosmos. The exploration of Pluto's orbit and its role in the solar system will continue to shape our understanding of the universe for years to come. Pluto's orbital behavior and its distinctive interactions with Neptune have long been a subject of fascination and intrigue within the scientific community. Despite its designation as a dwarf planet, Pluto continues to pose a challenge to our comprehension of planetary dynamics. The fact that Pluto's orbit intersects Neptune's, yet a collision is avoided, highlights the complicated nature of gravity and orbital mechanics in our solar system. One of the most fascinating aspects of Pluto's orbit is its resonance with Neptune. This resonance, known as a 3:2 orbital resonance, means that for every 3 orbits Pluto completes around the Sun, Neptune completes 2. This carefully synchronized relationship ensures that the two bodies never come too close to one another, despite their crossing paths. Pluto and Neptune are essentially locked in a cosmic dance, where their orbits are set in such a way that they never collide. This unique gravitational relationship is an excellent illustration of the accuracy and balance in celestial mechanics. The forces exerted by Pluto's gravity and that of Neptune work together to maintain a stable orbit for both. Without this resonance, Pluto's orbit could have been disrupted, potentially leading to a collision or other significant perturbations in its trajectory. Appreciating this interaction is crucial for astronomers, as it provides insight into how celestial bodies can maintain stability even when their paths seem chaotic at first glance. Moreover, the Kuiper Belt, a region beyond Neptune, is a treasure trove of icy bodies and dwarf planets. Pluto is the largest known object in this belt, and its orbit provides valuable information about the conditions that prevail in this distant part of the solar system. The Kuiper Belt objects, KBOs, and trans-Neptunian objects, TNOs, are remnants of the solar system's formation, and their study allows us to peek into the conditions that existed billions of years ago. Space agencies like NASA are now directing missions toward studying these far-off regions. NASA's New Horizons mission, which carried out a 2015 flyby of Pluto, provided us with unprecedented images and data about Pluto's surface and atmosphere. The findings of this mission revealed frozen nitrogen plains, towering ice mountains, and a complex weather system, suggesting that Pluto is a geologically active world. It also showed the diversity of Pluto's moons, providing clues about how moons form and how new ones may emerge in the outer solar system. The New Horizons mission also illustrated the growing capabilities of modern space exploration. Such missions not only expand our knowledge of distant celestial objects like Pluto, but also pave the way for more ambitious explorations into the Kuiper Belt and beyond. The success of this mission has sparked renewed interest in exploring these faraway regions and may inspire similar missions to other objects within the belt. Despite the apparent stability of Pluto's orbit, its eccentric and tilted trajectory raises questions about the long-term dynamics of the solar system. The fact that Pluto's orbit is so different from the nearly circular orbits of the 8 major planets offers astronomers a fascinating puzzle. Its inclined and elliptical orbit serves as an indication that our solar system doesn't work as neatly as it might seem at first glance. The chaotic behavior exhibited by Pluto's orbit could have profound implications for our understanding of planetary formation and evolution. This chaotic motion challenges the traditional models of a stable, well-ordered solar system and pushes scientists to reconsider long-held assumptions. It suggests that gravitational interactions, past collisions, or the presence of yet undiscovered bodies could have influenced Pluto's current trajectory. Some hypotheses even propose the existence of a distant, massive object, commonly referred to as Planet 9, whose gravitational pull may be subtly shaping the orbits of Pluto and other trans-Neptunian objects. Furthermore, Pluto's dynamic environment reveals that even distant, icy worlds are not static or dormant. Data from New Horizons showed evidence of cryovolcanism, surface renewal, and complex atmospheric processes. This unexpected activity implies that internal heat sources, perhaps caused by radioactive decay or tidal interactions in the past, could still be at work. If such geological and atmospheric complexity can exist on Pluto, it raises the question, what other surprises might await us on similar distant worlds? In addition, the information gleaned from studying Pluto and the Kuiper belt informs not only our understanding of the outer solar system but also enhances models used in the search for exoplanets. Many exoplanetary systems discovered by missions like Kepler and TESS show signs of orbital resonances, eccentric orbits, and planet migrations, phenomena we are now learning to identify and interpret through our studies of Pluto and its neighbors. The comparative study of these distant objects allows astronomers to draw parallels between our solar system and others in the galaxy. In this way, Pluto serves not only as a scientific puzzle in its own right but also as a key to unlocking broader cosmic truths. As humanity looks farther into space and technology continues to evolve, missions to other dwarf planets, such as Eris, Haumea, or Makemake, may become feasible. Each mission will build upon the foundation laid by New Horizons and other exploratory efforts, enriching our understanding of the solar system's diversity and complexity. In summary, Pluto's orbit is more than just an astronomical curiosity. It embodies the intricate balance of forces that govern celestial motion and reveals the hidden intricacies of our solar system's formation and evolution. Its resonance with Neptune, its unexpected geological activity, and its position within the Kuiper belt all point to a solar system far more dynamic and mysterious than once believed. By continuing to study Pluto and objects like it, we not only explore the frontier of our celestial neighborhood but also lay the groundwork for understanding the nature of planetary systems throughout the universe. The legacy of Pluto's exploration is one of discovery, curiosity, and the relentless pursuit of knowledge, qualities that define humanity's journey among the stars.